Okay, so my talk is regarding an empirical study on the optimizations in the Graal compiler. Even though the optimization is commonly adopted in nowadays, managed runtime is actually not being studied in the literature. So the goal of this study is to explore what are the reasons and actions for the optimizations, and how frequently they are triggered. Is there any compilation efforts being wasted because of the optimizations, and what kind of enhancement we can apply in the presence of the optimization? So to this end, we actually developed a profiler that collects the optimization's behavior in the HotSpot equipped with the Graal compiler. The Graal compiler is actually developed by the Oracle Labs and is an alternative option for the C2 compiler. Before we go into the actual study, I'd like to briefly talk about the optimizations, let's say introduction to the optimization. So when we have a Java bytecode program, the HotSpot first uses its interpreter to interpret, and the frequently executed part of that is then fed to the dynamic compiler to perform dynamic compilation. The dynamic compiler emits binary code that can be executed directly on the hardware, and when it encounters some issues, it will then trigger the optimizations and bear to the interpreter and continues execution there. Indeed, the HotSpot actually applies a tiered compilation strategy that involves two compilers, the C1 compiler and the C2 compiler. If we compare these two compilers, the C1 compiler actually might have a relatively faster compilation, while the C2 compiler might emit code that runs much faster. Indeed, the C1 compiler actually can emit code that is with no profiling logic, with limited profiling logic, and with full profiling logic. These three different kinds of compilation, along with the compilation by the C2, forms the four different compilation level inside HotSpot. So in common case, when we have a method that is being executed for a certain amount of time, is then fed to the C1 compiler to perform the compilation with full profiling logic. And then if the execution count of it exceeds another threshold, is then fed to the C2 compiler to perform a final compilation. While the C2 compiler might be busy, meaning that there are actually many unhandled compilation tasks to the C2 compiler, then instead of fed into C1 compiler with the full profiling logic, it actually fed to the C1 compiler with limited profiling logic, just to postpone the, let's say, the spamming up to the C2 compiler. So in terms of achievable method, meaning that there might not be any significant difference between, in terms of performance, between the code compiled by the C1 compiler and between the code compiled by C2 compiler, then it's simply compiled by the C1 compiler. So as a matter of fact, as I said, the Graal compiler is an alternative solution for this, let's say, replacement for this C2 compiler. So we could, and it actually applies quite many speculative optimizations that's profile guided. So our study actually is based on this setup that we have the C1 compiler, also the Graal compiler. So here I will talk about several speculative optimizations that are applied by the Graal compiler. Of the first one is the unreached code. If we look at the code snippets on the left-hand side, we do have, let's assume that the then clause here has a 0% possibility to be taken. And we could actually transform this code snippet to the code on the right. So if the condition is met, we then bear to the interpreter and will not continue execution in the binary code. With this, we can actually use the constant value of y to in the subsequent compilation. So yet another one is the inlining of polymorphic cosi, which is quite important in Graal. So let's assume that we do have this interface cosi, let's say invocation to an interface method, and we have two different implementation to this interface method. And let's assume that we, with this cosi, we have a receiver type profile that consists of both A and B. Then we could transform this into a code snippet like this. So we actually test against the class of A, whether it's being A or B, if class of the object, whether it is being the class A or class B. In case there is, then we actually proceed with the concrete implementation, or otherwise bear to the interpreter. The third one is a profile guided instance of test. So here I show you the hash operator in Scala. is actually kind of like inlined by the Scala compiler to the when generating the bytecode. So it tests against the receiver of this hash operator whether it is an instance of number. If it is, it then invokes a library method inside the Scala library. Otherwise, it just invokes the hash code method of the corresponding Java class. So indeed, if we assume that there is some receiver type profile for this instance of operator, let's say instance of bytecode that it consists of receiver type that of the single type being string class, then we can actually create some optimizations like this. So we test against whether this class is a string class. If not, we build an interpreter. If yes, we actually proceed. So we could actually use this information to evaluate the outcome of the instance of to be false here, and then we can further optimize it into some code like this. So in fact, this kind of built-in interpreter invocations are very important and actually are of our interest to look into because it kind of like represent the speculation by the dynamic compiler. The dynamic compiler normally assumes that this kind of speculation will not fail or is very unlikely to fail. So in case it does fail, it just means that it might be a phase change of the program. This is how the compiler thinks at the moment. But also, it might be just a glitch. It could be a very rare case and will not happen again. So if it is a glitch, it actually means that we might actually try to reuse the compiled code as much as possible because the rare case will not happen again. But if it is a phase change of the program, we might actually try to discard this compiled code because it does not necessarily reflect the accurate program behavior in the subsequent execution. And we might actually consider try to reprofile these kind of actions and reprofile this method. So indeed, the HotSpot actually provides quite many built-in actions that allows the compiler writer to choose from. So here I show you the decision tree for the compiler writer, how to choose between these kind of actions. So the first question we want to ask is that if we want to discard the compiled code. So if we don't want to discard the compiled code, then we go for this non-action. So otherwise, if we really want to discard the compiled code, we also ask when we want to recompile the code. So if we want to schedule the recompilation immediately, then we go for this invalidates recompiled method actions. Or otherwise, if we never want to recompile this method again, we go for this invalidates stop compiling actions. If we want to take some time in the interpreter and then to recollect the profile for this dedicated method, then we go for this invalidate reprofile method. So let's take an example, the inlining of polymorphic call sites. So basically, for this, when the optimization is hit, we kind of like know that there is a new receiver type incoming, and we might think that it might be just a new phase, so it could be even more receiver types, or let's say unseen receiver types. So one solution is that we go for this invalidates reprofile here and try to recorrect the receiver type profile for this dedicated polymorphic call site. The HotSpot actually provides yet another actions that's like recompile if too many deops, which relies on a built-in deoptimization profile that is let's say go for the non-actions at the very beginning, and then if there is enough deoptimization to be seen for this particular site or method-wise, then you go for this invalidates recompile. And if there is already a recompilation for this dedicated sites, then you go for the invalidates reprofile. So indeed, the Graal compiler doesn't use these two because they actually try to maintain very accurate and go for this non and invalidates recompile, invalidate reprofile for each particular optimizations. And to this end, we actually developed this Deoptimization Profiler that is targeting the HotSpot VM equipped with C1 compiler and the Graal compiler. This profiler instruments directly at the intermediate representations level, and it reports the optimization actions and reasons, as well as the originating bytecode. So this information actually identifies the optimization sites in our profiler, and we apply this profiler in Decouple and Scala bench workloads. Here I show you the immediate optimization sites for each workload. And as you can, the bigger the pie chart is, the more the optimization sites there are. So here, the recompiling profile is just abbreviation for the invalidates recompiling invalidates profile. If we look at the largest one, the J-SOAP, indeed we have like 22,000 of the emitted deoptimized sites being, let's say, emitted, and most of them are being invalidated profile. If we take a look at those that are actually triggered, so out of these, almost 95% of the optimized sites being in the invalidates profile category, there are only 2% out of the whole are being triggered. So the same behavior applies to other workload as well. So indeed, the first takeaway message that we'd like to give away is like speculation works as expected. So in fact, there are only 2% of the invalidates profile that the optimization sites are triggered on average. And we actually do evaluations on the speculative optimizations. So by disabling some of them, we actually observe a 26% degradation in steady-state performance. So we have gone through the good parts and we move to the bad parts. So let's recall that the dynamic compiler actually wants the optimization should be rarely triggered and not repeatedly triggered because we don't want to step in the same trap again. However, we found out that 12% of the triggered deoptimization sites are repeatedly triggered. The reason for this are actually twofold. One could be that there are different threads running the same version of the compiled code and hit the same deoptimization sites, and hence our profiler reports that there are actually repeated triggering of these sites. This is harmless, but the other could be very harmful or more serious, let's say. It's basically because the recompilation is unable to eliminate the trigger deoptimization site. So in a recompiled code, it actually might still hit the same sites. So this could be very dangerous. Here, actually, if we look at the optimization counts in a timely manner, in a timely scale, actually, we might expect that we could have many deoptimization at the very beginning, and then it kind of converges to zero as the count goes. However, it's not in the case of the Scala doc. We observe in Scala doc quite many repeated deoptimizations. And it's basically because of this dedicated method, HotSpot.element hash code being inlined into other methods. So here I show you the code snippets of this. Basically, we do have this element hash code, include this hash operator that we discussed before, and we do have this compute hash that kind of like invoke this method. So as we actually go through, this hash operator can be optimized into this by taking into account the, let's say, the speculative optimizations for instance of. Then when we inline this method into compute hash, we could actually end up with some code similar to this. And it's basically what we observe. There is a single receiver type profile for this instance of being the string class, and then when it gets executed, if it is of the type string, it will continue execution. If not, it will fail to the interpreter. And the issue happens when we hit this fail to interpreter. So basically, when we hit this fail to interpreter, instead of going directly inside the inline one, it actually goes to the very beginning of the hash set compute hash. So we go through this interpreted hash set compute hash. And then when we re-execute this invocation, then we might actually go through a C1 compiled that's like without profiling version of this hash set element hash code. So this is like without any deoptimization sites and cannot update the receiver type profile. So to summarize this issue is like we actually have a recompilation based on an outdated profile, and it's more due to inlining plus improper deoptimization targets that's like points to the caller instead of points to the inlined callee. So the reason of that are actually twofold. Callee compiled at a different compilation level, like the example we saw just now, or it could be also the callee compiled with different applied optimizations. For example, there could be a polymorphic call site that being inline in the callee, but not in the caller, and I actually create a bug report for that. The other cases that might lead to a recompilation based on an outdated profile is like in a concurrent program. And here I use an example to illustrate this problem. Let's take a look at, let's assume that we have and produce a single consumer program, and that the consumer is like being stressed too much, and it will never hit this then close. So we could actually, we could actually transform it into the code snippets like on the right. So if this then close is hit, we then bail to the interpreter. However, because it could occasionally be triggered and bail to the interpreter. However, after the optimization, it's very likely that the other producer might actually spam already the queue and then push a lot of items inside. So it will eventually hit to this item greater than 0 after the optimization. So it will not update, let's say, it will not properly update the branch profile of this branch extraction. And it's actually happening in the actors benchmark when it is using the Java Utu concurrent package. So the takeaway message of this is that, yeah, we have to update the profile properly. And some solution might be we directly inject the profile at the optimization already. So although this seems quite buggy, but it actually does not have a big impact on the performance. And we were actually thinking about some more general idea how to enhance the let's say the startup performance or whatever in terms of in the presence of the optimization. So the conservative thinking that is used by the runtime or by the compilers, normally when we hit the optimizer, we think that it just can be a phase change, and then we have to reprofile and then to update the profile and recompile it again. However, with speculative thinking, that we might think, okay, this is just a rare case happening. We try to tolerate it for a second time and then to see what it happens. If it appears again, we kind of like then do the actual actions. So the goal of this is like we don't spam the compilation queue for the compiler and then make the compiler to compile the other methods first. So with this, we actually developed, let's say, with very minimal efforts, adaptive the optimization strategy that is like based on our profiler. And kind of like switch amongst different actions. And we actually achieved quite some speed up, like 6.4% in the single core system. And as you can see, actually, there are some benchmark, some workloads that are very favorite of this tolerance of the optimizations. This is only, let's say, tolerating for a single time. So, the final takeaway message is that tolerating the optimizations actually helps in this way, although it can't be amortized in a multiple setup or in a steady state. And to conclude, in Graal, invalidates we provide the optimization that is like used for implementing the speculative optimizations kind of like dominates, but it actually rarely triggers. However, we have to ensure that when it is triggered, we want to update the method profile such that the recompilation actually will not step in the same trap again. And at last, actually, we observe 6.4 of the computation resource being saved in the single core setup by tolerating a single deoptimization per site during the startup. So I would say with this, I conclude my talk, and I'm happy to take your questions.
This is super interesting. So it mirrors a lot of experiences we had in JavaScript core. One of the main optimizations for deoptimization that we have is we allow it to be relatively aggressive recompilation cycle initially with fairly aggressive exponential backoff, i.e. requiring exponentially more reprofiling every time a function deopts. Do you guys have anything like that?
So in HotSpot, it did whenever it hits this kind of Deoptimization will always trigger this reprofiling. So it takes some, it kind of like how it implements it is like resets the hotness counters of the method. So it allows the interpreter for retraining it for a certain amount of time.
Sure, but does it have exponential backoff if you have a recomp cycle on a function? So you're recompiling, you deoptimize the function the second time, then you require twice as much profiling. You do it a third time, you require 4 times as much profiling.
Okay, now I got that. I don't think there is. So they basically still reuse the same hotness counter for that, I would say. So hotness threshold. So you're saying that you actually allows for more, let's say stay there for more time for training the data reflects the, let's say, profile for the program for a longer time when it hits the optimizer again.
Yes. So the point is that then if it's very common that I shouldn't say very common. You'll see functions that recompile once, right? Because the first time you compiled them, you got something wrong, and then it's fine the next time. So having exponential backoff means that we can have a much lower threshold for how long you reprofile those guys, while having exponentially increasing thresholds for the guys that are trumped.
Okay, I see your point. So the thing that I might not get clear is like, for example, in hotspots, if we do have a, let's say, normally when we hit the optimizers, the next time when it compiles, the optimizer site might disappear. So in this case, the JavaScript one is like they still generate this Deoptimization Sites, or it might actually.
It'll probably disappear because the new profiling will tell you you don't need it. But if you
right,
have
exactly.
Functions, say 10,000 bytecodes, then
so
the initial compile will have many places that you deoptimize.
All right.
And then you recompile, so that some of them disappear due to more profiling. But there may be still regions of the code you haven't even executed yet. You have to be able to know what the real profile is. So exponential backoff dynamically adapts to how crazy a function is. If the function's really crazy, then we profile it a lot more.
Right. Yep. So thanks for these comments. And also the other thing that I was thinking in the, let's say, as a future work is like, so basically when we actually hit the opt, we actually generalize this code, and it includes, let's say, more, and then it's not very speculative anymore. And then in some sense, I was thinking about if we have this change phase, then I would like to make, let's say, very speculative optimizer dedicated for this phase. So I kind of like wipe out the profile of the preceding execution. So do you think that kind of things could be worth trying?
We do it when we tier up. So our equivalent of C1 may perform a speculation.
Right.
And the thing is that when we then go from C1 to C2, we will have seen some recompilations in C1, but we have a forgiveness on some of them when we go to C2. Additionally, you mentioned when you deopt at the deopt site collecting more profiling, we do that. We actually snapshot variable values.
Right. Okay.
So when you recompile the thing that deoptimized previously, we actually have richer information about what's going on there than we would have had just from the profiler alone. Because the strongest profiler in our system is actually the profiler in the deoptimization site.
Yeah, that makes sense, actually.
Okay, so let's thank the speaker again.